Good morning, students. In the last session, I have discussed about hydrogen atom spectrum, quantum numbers, and their significance. In today's class, I will be discussing about the nodal plane, and shapes of sp and d atomic orbitals. After that, I will be discussing about various principles which are used for filling up of the electrons in the atomic orbitals. That is, we will be studying about the rules for filling the atomic orbitals. So, let us begin today's class. First, we'll see what is a node. Node is the region where the probability of finding an electron falls to zero. See here, this is 1s atomic orbital. Here you are not observing any node. This is also 2s atomic orbital. But see here the third diagram at the center portion. This we call as a node. That is, it is the region where we are having the probability to find the electron which is zero. That is, probability of finding an electron at this region will be zero. That region is called as a node. Next one is a nodal plane. Nodal plane is the here the lobes of the orbitals are separated by the plane that contains the nucleus and is perpendicular to the other axis. Such a plane is called as a nodal plane. See the diagrams here. These are called as lobes. These are the lobes of the orbitals. These lobes are separated by a plane. This is called as a plane. You can see here like a rectangular sheet. This is nothing but a plane. The lobes of these orbitals are separated by a plane that contains the nucleus. Here there will be a nucleus and is perpendicular to the other axis. This plane will be perpendicular to these axes. Such a plane is called as a nodal plane. For example, see here pz orbital. This is a pz orbital. These are the lobes. These lobes are separated by this plane. You can see here imaginary plane like a rectangular shape here. These lobes are separated by this plane and it is containing nucleus, and this is perpendicular to yx. Here yx is the nodal plane for the pz orbital. So next we'll move to shapes of sp and d orbitals. First we'll see the shape of s orbital. Here the shape of s orbital is spherical. That is, probability of finding an electron is equal in all directions. Keeping in view that the atoms are three-dimensional, the probability surface diagram of s orbital is spherical. See here, the shape of s orbital is spherical, and finding the that is probability of finding electron is equal in all directions. That is, we can find the electron in all the directions x, y, z. That is, the probability of finding the electron is equal in all the directions, and the shape of s orbital is spherical. Next is a shape of p orbitals. For L is equal to 1, M is equal to minus 1, 0, plus 1. It represents three orientations of p orbitals. We know that three orientations of p orbitals are px, py, and pz. These are the three orientations of p orbitals. That is, when L is equal to 1, M is equal to minus 1, 0, 1, it represents that p orbital contains three orientations. You have to keep it in mind. Those three orientations are px, py, and pz for the quantum number minus 1, 0 and plus 1. If for L is equal to 1, M is equal to 0, then it is labeled as a PZ orientation. It is considered as a PZ orientation, and electron has the form of dumbbell along the x-axis. Sorry, along the z-axis. When L is equal to 1, M is equal to 0, then it is labeled as a pz orbital, and electron will be having a dumbbell shape along the z-axis. This is a z-axis. You can see here in the diagram. This is a z-axis, and you will be having it will be having a dumbbell shape along the this z-axis, and the dumbbell shaped lobes of high probability are separated by a nodal surface in xy plane. See here, this is the x plane and it is the y plane. So we know that this is a dumbbell shape along the z axis. These are the two lobes. This is one lobe and this is another lobe. So these lobes are separated by this xy plane, in the xy plane. Other two orbitals, that is px and py, have also found to have a dumbbell shapes along x and y axis respectively. See here, this is a px orbital. Here also you can see the dumbbell shape along the x axis. This is the x axis. Here in the px orbital, the dumbbell shape will be along the x axis, and in the py orbital the dumbbell shape will be along py axis, and in the pz orbital the dumbbell shape will be along the pz orbital, that is along the z axis, and the lobes are separated by this xy plane. So next one is the shape of d orbitals. If for L is equal to 2, then M is equal to minus 2, minus 1, comma 0, comma plus 1, comma plus 2. This represents that there will be 5 orientations. That is for quantum number value, that is minus 2, comma minus 1, comma 0, plus 1, comma plus 2. It represents that there are 5 orientations of d orbitals. There are 5 orientations of d orbitals. Those are dz square, dx square minus y square, comma dxy and dyz, dzx. These are the 5 orientations of d orbitals. Probability surface diagram of three orbitals, that is dxy, dyz, dzx, and have four lobes of high electron density in xy, yz and zx planes respectively, with each lobe bisecting the principal axis into two equal halves. What they are telling in the surface diagrams of the three orbitals, that is dx, dxy, dyz, dzx. See here, this is a dxy, dyz and dxz orbitals. You can see here four lobes are there. These are the four lobes, and these four lobes having high electron density in xy plane and yz plane and zx planes. For dxy, this is a dxy orbital, the electron density is high in xy plane. This is the x plane and this is y plane. The high electron density is in xy plane for dxy orbital, and the lobe will be bisecting the principal axis into two halves. This is the lobe, and it will be bisecting the principal axis into two equal halves. You can see the plane here, it is bisecting into two equal halves. Similarly for dxy orbital, the electron density will be high in the YZ plane. This is a Y plane, this is a Z plane. So this is about the shapes of s, p and d orbitals. Next we'll move to rules for filling the atomic orbitals. The filling of the electrons into the orbitals of different atoms takes place according to three principles, that is Aufbau principle, Pauli's exclusion principle and Hund's rule of maximum multiplicity, and on the relative energies of the orbitals. That is, we can fill the electrons according to the principles, that is Aufbau principle, Pauli's exclusion principle, Hund's rule of maximum multiplicity, and based on the relative energies of the orbitals. And the three principles we have to study are, that is Aufbau principle, second one is Hund's rule of maximum multiplicity, third one is Pauli's exclusion principle. So first we'll see the Aufbau principle. Here the word Aufbau in German means building up. The building up of orbital means filling up of the orbitals with electrons. That is, the word Aufbau is from the German word which means building up. Building up is nothing but a building up of the orbitals, which in turn means that is a filling up of the electrons within the orbitals. It is nothing but Aufbau is nothing but a filling up of the orbitals with the electrons, that we call it. The main principle behind this is that is filling up of the orbitals with the electrons. This principle states that the orbitals in an atom are filled up with the electrons. That is, here we have to fill the orbitals in an atom with the electrons. In other words, electrons first occupy the lowest energy orbitals available to them and enter into higher energy orbitals only after the lower orbitals are filled. That is what this principle states. It states that we have to fill the orbitals of an atom with the electrons in such a way that first we have to fill the lower energy orbitals. Once the lower energy orbitals are filled with the electrons, then we have to go for the higher energy orbitals. Until then, we should not fill the higher energy orbitals with the electrons. That is what we have to do. We have to fill the lower energy orbitals first, then we have to go for the higher energy orbitals. The order in which the energies of the orbitals increase and hence in which the orbitals are filled is as follows. That is, the order in which we have to fill the orbitals with the electrons and the energies of the orbitals are given below. See here, the order we have to fill is first we have to fill the 1s orbital, next 2s orbital, next 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, so on. That is, this is the order of filling of the orbitals. It is the order of filling of the orbitals. See here, this is the order of filling of the orbitals. You have to start from 1s atomic orbital. First you have to fill the 1s atomic orbital, then go for 2s atomic orbital, then go for 2p, 3s, 3p, 4s, then move for 3d, 4p, 5s, then for 4d, then 5p, 6s, 4f, 5d, 6p, 7s, then after 7s you will be coming across 5f, 6d. In this way you have to fill the orbitals. You have to fill the orbitals in the order of increasing energy. That is, you have to fill the lowest energy orbitals. You have to fill the lowest energy orbitals first. Then after filling the lowest energy orbitals, you have to go for the higher energy orbitals. You have to move for the higher energy orbitals. Then the order of the energies of the orbitals are like this here. See here, this is the increasing order of the energies. First energy level, that is orbital energy level, is 1s. Second one is 2s, then 2p, 3s with one orbital, 3p with the three orbitals, 4s, 3d, 4p, 5s, then 4d with 5 orbitals, 5p, 6s, and 4f. In this way, we have to fill the orbitals with the electrons. That is, we have to fill the orbitals with the electrons in the order of lower energy orbitals to the higher energy orbitals. This is about the Aufbau principle. Next one is Hund's rule of maximum multiplicity. Here, Hund's rule indicates how electrons pair up in the various orbitals. There we have studied about filling up of the orbitals with the electrons. But here we are studying about pairing of the electrons. We are studying about pairing of the electrons in the orbitals. According to this principle, pairing of electrons in the orbital belonging to the same subshell does not take place until each orbital belonging to that subshell has got one electron each, that is singly occupied. What it states, the principle states that we have to pair up of the electrons, or we have to pair the electron in such a way that until each orbital gets one electron, we should not pair the electron present in the orbital. That is, first we have to fill the orbital with one electron each. Then we have to start pairing of the electrons. That is what we have to do. We have to fill the electron in each orbital. Then after filling the electron in all the orbitals, then we have to start pairing of the electrons. Once the orbitals are singly occupied, then we have to start pairing the electrons. First we have to singly occupy the orbitals. Then once all the orbitals are singly occupied, then we have to start pairing of the electrons. Electrons are distributed among the orbitals of the given subshell in such a way that they give maximum number of unpaired electrons and the same direction of spin. That is, we have to distribute the electrons among the orbitals in such a way that we have to get maximum number of unpaired electrons, and the electron should have same direction of spin in such a way that we have to fill the electrons in the orbitals. Thus, the orbitals at a subshell are filled singly before they begin to pair up. So, first we have to singly fill the electrons, then we have to start pairing up of the electrons. In other words, pairing must begin with the entry of second electron in S subshell. That is, see here, this is a S subshell. Here what they are telling, that is, pairing must take when the second electron enters in the s subshell. That is what we are telling, we have to fill up the orbital with one electron. Then once the orbital is singly occupied, then only we have to start pairing of the electron. This is s orbital, so it is filled with one electron. It is singly occupied. So after singly occupied, then we have to start pairing it. So we are writing another electron. So what they are telling, second electron in the s subshell. Pairing in the s orbital starts with the second electron. That is, pairing in the s orbital is starting with the second electron. Similarly, pairing in the p subshell starts with the 4 electron. We know that there are 3 orbitals in the p subshell. See here. We have 3 orbitals in the p subshell. Once we have to write the electrons or fill the orbitals with the electrons, we are filling the orbital with one electron each. Pairing in the p orbital starts with the fourth electron. This is a fourth electron. So pairing in the fourth p orbital starts with the fourth electron. Pairing starts with the fourth electron in the p subshell. Next one is the d subshell. We know that in the d subshell we have 5 orbitals. We have 5 orbitals in the d subshell. So first we have to occupy the orbitals with single electrons. So write the single electrons here. So third electron in the third orbital, fourth electron in the fourth orbital, fifth electron in the fifth orbital. So first all the orbitals are singly occupied. Then what they are telling, pairing in the d subshell starts with the sixth electron. These are the 5 electrons. Then pairing starts with the sixth electron. Similarly, in the f subshell, pairing starts with the eighth electron. And according to this rule, arrangement of electron for few elements is given in the below table. See here, these are the elements. I have taken example of carbon and nitrogen. We know that atomic number of carbon is 6 and nitrogen is 7. So first we have to write the electronic configuration. Electronic configuration for carbon is 1s2, 2s2 and 2p2. So we have to fill the electrons in the orbitals. We have 1s orbital, 2s, 2p. First we have to fill the 1s orbital. Here first we have to fill one electron, then we have to start pairing the electrons. We have 2 electrons here in the 1s orbital, so we have to pair the electron. So we have 2 electrons, then 2 electrons in the 2s orbital. Here 2 electrons in the 2p orbital. Here no pairing occurs. Whereas for nitrogen, we have electronic configuration 1s2, 2s2 and 2p3. Here again in the s orbital, we will be having 2 electrons. First we will fill the orbital with 1 electron. Then once the orbital is singly occupied, we have to start pairing. So once 1 electron is filled, we have to fill the orbital with another electron. Then similarly in the 2s orbital, again we have 2 electron. First you have to write single electron, then you have to pair it with the other electron, because we have 2 electrons in the 2s orbital. First we have to write single electron, then only we have to start pairing. In the 2p orbital, we have only 3 electrons. We have only 3 electrons. So, you have to write, that is, you have to singly occupy all the orbitals. So, write all the 3 electrons in a orbital each. There is no other electron to pair up with these electrons. So, in the 2p orbital, you have only 3 electrons. So, you have to keep it in mind, that is only the once we occupy the orbitals with a single electron, after that we have to start pairing the electrons. Unless until we singly occupy the orbitals, we should not start pairing up of the electrons according to the Hund's rule of maximum multiplicity. So next we will move to Pauli's exclusion principle. This principle was given by scientist Wolfgang Pauli. According to this principle, only two electrons may exist in orbital, and these electrons must have a opposite spin. This principle was given by a scientist Wolfgang Pauli, and according to this principle, we have to fill the fill only two electrons in each orbital. We cannot fill the orbital with more than two electrons. And both the electrons, that is both the electrons which are present in the orbital, must have a opposite spin. They should have a opposite spin. This means that the two electron can have the same value of three quantum numbers, that is n, l, and ml. These are the three quantum numbers that the two electrons can have, but must have opposite spin quantum number, that is they have spin in opposite direction and the value of plus half or minus half. That is, they should have a opposite spin. Both the electrons should have opposite spin with the values either plus half or minus half. Hence, K shell can have only one subshell, that is S, and can have only S subshell, and it has the capacity to accommodate only two electrons. K shell can have only one subshell, that is S subshell, and it can accommodate or it can have only two electrons in this S subshell. And L shell can have two subshells, that is S and P subshells, and can have the capacity to accommodate 8 electrons, that is 2 electrons in the S subshell and 6 electrons in the P subshell. That is L shell can have two subshells. One is S subshell, another one is a P subshell, and these two subshells can accommodate 8 electrons together. That is 2 electrons in the S subshell and 6 electrons in the P subshell, totally 8 electrons. And M shell can have three subshells, that is S, P and D subshells, and have the capacity to accommodate 18 electrons, that is 2 electrons in the S subshell, 6 electrons in the P subshell and 10 electrons in the D subshell. Here in the M shell we can have only 3 subshells, that is S, P and D subshells. And these 3 subshells together can have 18 electrons. 2 electrons in the S subshell and 6 electron in the P subshell. We know that P subshell have 3 orbitals px, py and pz. Each orbital can have 2 electrons. So totally 6 electrons in the P subshell and 10 electrons in the D subshell. We know that 5 orbitals are there in the D subshell and 5 orbitals can have 2 electrons each. So totally 10 electrons in the D subshell. So overall they can have 18 electrons in the M shell. Similarly, N subshell can have 4 subshells, that is S, P, D and F subshells, and have the capacity to accommodate 32 electrons, that is 2 electrons in the S subshell, 6 electrons in the P subshell, 10 electrons in the D subshell, 14 electrons in the F subshell. That is N shell can have four subshells S, P, D and F subshells, and all these together can have 32 electrons, 2 electrons in the S subshell and 6 electrons in the p subshell, 10 electrons in the d subshell, and in the f subshell we know that there will be 7 orbitals, and so each orbital can have a 2 electrons, so totally 14 electrons in the f subshell. So all together can have 32 electrons in the n subshell. So this is a representation of that. Name of the shell KLMN shells. Subshells will be having 2 electrons each. That is, S subshell has 2 electrons in the K shell. We know that here K shell will be having only S subshell, and S subshell can accommodate only 2 electrons. So total number of electrons in the subshell will be 2. So for L shell, the possible subshells are S subshell and P subshell, and S can have a 2 electrons and P can have a 6 electrons. So total electrons will be 8. M shell can have a 3 subshells. The possible subshells are S, P and D. S subshell can have 2 electrons, P subshell can have 6 electrons, D subshell can have 10 electrons. So total electrons in the shell will be 18 electrons. The last one is a N shell. N shell can have these 4 subshells, that is S subshell, P subshell, D subshell and F subshell. S subshell can have 2 electrons, P can have 6 electrons, D will accommodate 10 electrons, F will accommodate 14 electrons. So total electrons in the shell will be 32 electrons. So this was all about today's class. Here in the today's class we have discussed about node, nodal plane, shapes of sp and d orbitals. Then we have studied about rules for filling the atomic orbitals. In the rules we have studied about three principles, that is Aufbau principle, Hund's rule of maximum multiplicity and Pauli's exclusion principle. So further concept of atomic structure will be discussed in the next classes. Thank you.